We are live. Welcome back, everyone. It's been a minute, but I'm back. It is Ramadan. I'm very hungry. Actually, I'm not that hungry. I had a lot to eat this morning, but I did fall asleep at like 6 in the morning, so I'm kind of tired. It's a very gloomy day in, what month is it? March? It's a very gloomy March day in New York City. You can tell how with it I am. I took my USMLE last week. It went. We find out scores in about 8 days. And today, we're back to talking about physics, or as little physics as I know. This is our first of 2 sessions today, very special. It's the first time I'm doing this, but we have to wrap up the program because the program ends in April. The program ends on April 18th, I said, right? Right before you guys go on spring break, so that'll be the end of the first year of the program, and we will restart in August. Now, for everyone watching back home, I need your help with 2 things. Number 1, you need to tell me what videos I should make in the meantime when I'm at home. So like I can do, like deep dives in specific topics that people have trouble with. I could make like a whole 40-minute lecture about like the hormones because I can, because I'm just that guy, right? Or I could make like, interview type stuff where like it's just me talking to the camera about my experience with the MCAT, how to tackle the test, et cetera, et cetera. You guys let me know. And you guys let me know as well. All 4 people in the room right now. Also, the end of the month is coming, and I have the Buy Me a Coffee page that people have been donating to. If you guys are so generous, there's a Buy Me a Coffee page in the link in the description. You guys can donate a little bit of money. And I said that at the end of the month, 50% of all the proceeds will go to charity. But since it's Ramadan, and Ramadan is a month of charity, this month, all of the proceeds will be going to charity. And I'm going to decide the first charity that we give it to. So I've decided on Doctors Without Borders. And moving forward, every charity we give to will be some sort of medical charity since this is an MCAT course. So if you guys would like to donate to Doctors Without Borders through me or just donate yourselves, you can either drop some money in Buy Me a Coffee or just go to donate to Doctors Without Borders. So I'll be putting in all the money from the Buy Me a Coffee as well as a little bit of my own money as well. So you'll get the receipt for that if you're on the emailing list. So let's get started with Chapter 3 of Physics, Thermodynamics. All right. So thermodynamics is incredibly different than what we did in chemistry. Thermodynamics in chemistry was ruled by what? Pretty much one equation. And we know this like the back of our hand now. Like we understand this right, left, front, center, around the side. Like this thing could orbit around your head all day and you wouldn't even bat an eye because you're just like, I know what this is, right? But now we're in physics. There are laws. There are laws to abide by. Maybe that's why I hate physics so much, because I don't like the law. All right. So what are the laws of thermodynamics? There's something called the 0th law of thermodynamics. Like it's not the first, the second, it's the 0th law, because it's not technically like touted as a law in thermodynamics, but it's just true. So if you have a substance A that is in thermodynamic equilibrium with B, and this is a thermodynamic equilibrium, non-equilibrium as in they're changing into one another, right? And B is in thermodynamic equilibrium with C, then that means what? That A is in thermodynamic equilibrium with C. It's basically just a transitive property, right? And that's how my notes begin. If you look on my notes in the drive folder, you'll find that it's the first thing in my notes for Chapter 3. Okay, now, let's talk about temperature. Who knows what heat is? Who knows what heat is? It's a very simple question. What's heat?
Energy?
Heat is actually energy transfer, yeah. So when we talk about heat, we're talking about, specifically, the transfer of thermal energy from a hotter to a colder substance, right? Katy Perry would love this lesson. If you get that joke, you're a real one, and maybe a little older than most of the people who take this course.
No, come on, we grew up on that.
Really? Because that's when I was like 6 years old. right? That's like what, 2006, 2007?
Might have been a little later.
Maybe. I don't know. My memory's the dementia. It's coming. It's kicking. So, if the net heat flow is 0, then objects are in thermal what? Thermal equilibrium. I'm getting over a cold, if you haven't realized already. That's why I'm much quieter than usual. It's definitely not the starvation for the past 17 days from sunrise to sundown. It's the cold. Right? So let's define some constants. What is absolute zero? Absolute zero is the lowest possible temperature, right? It's where all matter stops. Like, matter's always moving. At absolute zero, all matter stops. That's a terrifying concept. Very, very scary. What's the coldest where was the coldest temperature ever recorded in the universe? Where did it happen? Happened here on Earth, actually. We made the coldest temperature ever. I think we came within like a fraction of a fraction of a fraction of absolute zero. If I'm not mistaken, it was at CERN, but I'm not 100% sure on that. It's at some insane like particle physics thing. Like they came very, very, very close to absolute zero. Yep, so absolute zero in degrees Celsius is negative 273.15. Right? What is it in Kelvin? It's 0. Right? And in Fahrenheit, for my Americans, which is almost all of you, it is negative 459.67 degrees, which is incomprehensible to me. That is cold. That is definitely cold. I wouldn't say that's a warm day. If I walked out and it was negative 459.67 degrees, I'm laying my ass in bed.
Anything in triple digits.
I'm going back to sleep. All right, some more constants. In all of these sort of units, what is the melting point of water? These are things you have to know off the top of your head. In Celsius, it's the melting point. 0. Right? Then, in Kelvin, 273. Technically 0.15, but you know, it doesn't matter, the 0.15. We don't really care about that. In physics, pi is equal to 3, so. What about Fahrenheit? 32. Right, 32. And the boiling point? So 100 degrees Celsius, 373.15 Kelvin, and 212 degrees Fahrenheit. What the hell, Fahrenheit? Stupid. There is an equation that might come up one time. If you do maybe 4,000 questions, it'll come up once. But it's in my notes, so I'm going to tell you. When you heat up a solid, it expands, right? There is a way to calculate that expansion, right? The change in the length, the expansion for a solid, is equal to alpha L delta T. A lot, right? It changes a lot, right? A lot. What is alpha? It is the constant of thermal expansion, right? And it's different for different solids, right? The L is the length, right? And then the delta T is the change in temperature, right? For liquids, it's a little different because it's not a length. What's it going to be? It's a volume, right? If that's a lot, what the hell is this? Exactly. And of course, the beta is the constant of, not thermal expansion, volumetric expansion. Sorry. My bad. It's not the constant, it's called the coefficient. Coefficient of linear expansion and the coefficient of volumetric expansion.
Sorry.
Yes. Yeah.
So when you heat up a solid and
Yeah.
you just give the equation on how to calculate it.
Right.
I do like practice MCAT questions on Kaplan or
Right.
Jack Weston. They're not like exactly what the AMC gives.
Right.
They're like similar material. Would that be considered like a high yield question? Because I haven't came across.
So the question was, is something like this high yield? And the answer is absolutely not. I think in the 7,000 MCAT questions, or 8,000 MCAT questions that I've done in my lifetime, this has come up maybe once.
Okay.
So very, very low yield.
I'm not. It's interesting.
Very, very, very low yield. All right, this is the highest yield part of this chapter. And honestly, something you already know. If you've watched our video about thermodynamics and chemistry, which you should, because it's definitely far, way freaking better than this lecture is going to be, you know about systems, right? So someone tell me what's an isolated system. It cannot exchange matter or energy with anything outside of itself, right? An isolated system. The system doesn't communicate, right? It is completely asocial, doesn't want to interact with you. Goodbye. No energy, no matter, nothing getting in or out. What's a closed system? So this is the most confusing difference. An isolated versus a closed system. An isolated system is in a cage. That cage is in a box. That box is in styrofoam. The styrofoam's at the bottom of the ocean. The ocean is filled with magma until it's all obsidian. And then you take that ocean and toss it into the stratosphere. And then it goes orbiting around the Earth, and it can never be seen again. That's an isolated system. A closed system is in your pocket, right? And you're not touching the pocket. You're not taking matter out of it, but you can feel it warm or cold in your pocket. So it can exchange heat, right? So it can not exchange matter, but it can exchange energy with the surrounding system, right? How do you create a cold system? Take an Erlenmeyer flask, HCl, drop magnesium in there, and the moment you drop the magnesium, put a cover on it. Put a cover on it. Put a really, really tight, airtight cover on it. None of the gas is going to escape. None of the magnesium is going to get out. None of the hydrochloric acid can get out. What are you going to feel happen to the vessel? It's going to get hot or cold. I forgot if it's an endothermic or isothermic reaction. I think it's exothermic because steam comes off, but then again, the steam is just the vapor. So maybe, I don't know. I forget. Open systems, whores. Giving it up to everyone. Just what? I should not be talking like this. It is the holiest month of the year. So they're walking around dropping coins everywhere, and like they're just yelling at everyone, and everyone's getting the smoke, and they're fighting people, and they're vomiting all over the place. So matter and energy and this and that going everywhere. Can communicate as freely as it wants. Right? And then we have state functions. And state functions are basically ways that we describe systems, right? There's a couple of them you need to know. Pressure, density, temperature, volume, enthalpy, and internal energy. I will write these down. Don't worry about it. Because you also need to know the symbols for all of them, which are pretty high yield. So we have pressure, which is capital P. Because what's lowercase p? Negative log. Yeah, pH. Negative log, right? Lowercase p is... Huh? Is momentum lowercase p in physics? Okay, then I forget. So in physics, it's momentum. And then in chemistry, it's negative log. All right, see, chemistry-minded, right? All right, density. Who knows the proper name for the symbol for density? Rho.
Which also looks like a P.
Yeah, it looks like a P, but I draw it like a little, At least I got one laugh. No, you're fine. I said I drew it a little, off to the wayside. Don't come at me. Don't come after me. I live in New York City. Other door. Temperature. Who knows the symbol for temperature? It's capital T. How you doing, man? What's going on?
Howdy. Sorry to interrupt.
You're good.
There was an issue with the USB-C. Do you mind if I...
Oh, yeah, please, go for it. Yeah. What's the symbol for volume? Capital or lowercase? Capital V, right? Then, enthalpy. A lot of people want to say delta H. Delta H is change in enthalpy. Enthalpy is a capital H. Internal energy. What is the symbol for internal energy? Internal energy in the system. E is overall energy. Do you know what the symbol for internal energy is?
I don't.
It is a capital U. It is a capital U. You guys know there's like U equals Q times V equations? That's what we're talking about.
Isn't that potential energy?
Huh?
Isn't that potential energy?
Capital P. Just like pressure. Well, PE. Capital P, capital E, potential energy, right? Did you need something?
I don't. The only thing is the image is going to pop up on the board in front of you, and I don't want to interrupt your video. Maybe you want to...
That's fine. I mean, you do what you gotta do. If it's just gonna take a minute, we can just like,
no,
yeah,
I just
totally.
need to see the image pop up.
Yeah, for sure.
Connection, and I'm good.
As long as it's not anything that I can't put on YouTube, I think you're gonna be okay. All right, so let's just while this fine gentleman is doing his work, let's just lecture out of the notes for a second. So then we have Gibbs free energy, which is of course G, not delta G, but G, and then entropy, which is S, right? And those are your state functions. And what's important about the state functions? It's the fact that we can use the state functions to describe a certain system at equilibrium or not, right? So if someone asks you, what's the internal energy of that system, you could answer them. And it's a quality of the system at a given point in time. And it can be changed through changes in the system. That's all we're saying, right? This is basically the idea of thermodynamics, right? However, why did I give you this entire sort of like discussion about things you probably already know? Because there's a difference. And this is a very, very quick, easy to pick out, high yield, this is high yield, question on the physics section, right? These are state functions. What's a process function? A process function is how you get from a certain state of these to another. So the temperature, right? Beautiful landscape over there. The temperature. Thank you so much. If we apply heat to the system, correct, the temperature is going to change. So if the temperature changes through the addition of heat, heat is a process function. It's something that causes a change in a state function. It's a path, exactly. So these are constants that can be changed, but they're changed by process functions, right? So there are multiple times that you're asked on the chem phys section of the MCAT where it says, which of these is a process function? And you're playing a game of odd man out. So if you know these, at one point I knew these by heart. I could memorize these to you. Pressure, density, temperature, volume, enthalpy, internal energy, Gibbs free energies, entropy. I could say it off the top of my head. So if you're asked which of these is a process function, it's whichever one of those isn't one of these, right? But another way to think about it is, which of these doesn't describe a system? Which of these doesn't describe a physical thing that I can work with, like an experiment vessel or something like that? Does time, right? Does time describe a vessel? No, it doesn't. Does heat describe a vessel? No, it doesn't. All of these do, but those don't. Does that make sense?
Would a process function be like delta H also or no?
So a process function can cause a change in enthalpy. That's the thing. It can cause a change in enthalpy, right? What's the first law of thermodynamics? The change in the internal energy, right? So I'm going to dictate it in English and write it down in symbols, right? The change in the internal energy, so that's delta U, is equal to what? the amount of energy transferred in the form of heat to the system minus what? Minus the work done by the system. If you inject gasoline into a engine and you light it, and that gasoline puts heat into the engine, or puts energy into the engine, right? And the engine does work, the change in the internal energy of the engine is the heat minus the work done, right? However, this isn't super high yield. What is high yield, what they might ask you about, is the fact that despite all of this, the total energy of the universe is neither increasing nor decreasing. This refers to a system, not the universe as a whole, right? Now, just through some very quick, yo, you made it. Just through some very quick facts, let's talk about heat transfer, right? What is conduction? More specifically. Conduction happens through what? Solids, right? When two solids touch, right? So if I touch David's hand, right? And his hand is warm and my hand is colder than his is, how is the heat getting into my hand? Molecular collisions. Conduction is heat that is transferred through molecular collisions. The molecules in his hand are moving faster than the molecules in mine, and that's why the heat is transferred from his hand to my hand through conduction. Conduction.
I thought it was induction.
Induction is different. What's convection?
Air fryers.
Basically. So it's heat transfer via the motion of a fluid over a material, right? And what is a fluid? It's a liquid or a gas. Gases are technically fluids for some reason, right?
Convection, you said?
Convection, like a convection oven. Blows hot air over a material, and it heats up your food, and then you got a yummy pound cake waiting for you on the table. I love pound cake. Yo, shout out pound cake, man. Maybe I'm just hungry.
Yeah.
What's radiation? I put Laura in an X-ray machine, and I just shoot her like 7 times in the head. Why does she die?
The bullets.
No, not actually shoot you. I shoot you with the X-ray.
Oh.
Because there's energy in what? In the X-ray beams, right? What kind of energy?
Waves.
No. What's that energy called? Electromagnetic energy. Radiation is the transfer of heat through electromagnetic energy. Or transfer of energy through electromagnetic waves. The most common thing that we do that is radiation is what? You go home,
Oh, microwave.
you microwave something, right? You microwave something. Why do microwaves have those little screens? So you look at a microwave, right? You look at a microwave.
The most detailed drawing I'll ever get from you.
So you look at a microwave, right? And then you put food in the microwave, and then you watch it go round and round, right? Like Daft Punk around the world, right? And then on the screen, what do you see? You see little holes, right? What are those holes there for? So the microwaves won't hit you, because the holes are small enough that when the microwave tries to pass through them with its wavelength, the wavelength is so large of the microwave that it gets trapped by the holes and it just bounces back. Right? Isn't that cool? So when your brown mom, when you're like 6 years old, is like, don't stand next to the microwave, you're gonna die. It's not true. Sorry, Mom. Hey, want to see what I named my microwave?
Fuck what? Motor.
I'll leave that to the viewers. 9,000.
Oh, fuck, that's 9,000.
There you go. Everyone's favorite thermodynamic equation of all time, Q equals MCAT. Also the MCAT's favorite. And honestly, that's all I have to say about thermodynamics because I'm not good at it. Well, one more thing. What is an isothermal process? Isothermal process is something that happens at the same temperature. There's no heat transfer, right? So for an isothermal, so we go back to this equation, right? Where delta U equals Q minus W, right? In an isothermal process, this equation becomes what? Q equals W, right? In an adiabatic process, in isothermal process, delta V is 0, right? There's no change in the volume. We talked about the thermal expansion, blah, 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 whatever. In an adiabatic process, where the heat is 0, the heat exchange is 0, this becomes 0, which means delta U equals negative W. So this is isothermal. This is adiabatic, right? Not adiabetic, right? Don't bring that shit near me. Not again. Isovolumetric. Sorry. I said delta V is 0. Delta U is 0 here. My bad. I just didn't read my notes properly. My handwriting is bad. Isovolumetric, delta V equals 0. So isovolumetric, you have delta U equals Q. How do we understand that? Well, think about a piston. How does a piston do work? It changes the volume of the vessel, right? That's how a piston does work. So if you don't change the volume, there's no work done, which means delta U equals Q. This is isovolumetric.
Can you repeat that one more time?
Right, so the isovolumetric process where the delta V equals 0, right? If you look at a piston, the way that the piston does work is that it slams into this container, it decreases the volume, and it springs back up. And the amount of work done is how much the volume changes, how much it pushes the piston, and the piston turns something, blah, blah. That's the work that's done. You have no change in the volume. There's no work done. So the work becomes 0, so delta U equals Q. Right? And last is an isobaric process where the delta P equals 0. That has an indeterminate equation. There's no way to really sort of derive that unless you did the experiment. So these are probably the three you need to know. But also, you'd need to identify them on a curve, right? So you're going to have a pressure-volume curve, right? Pressure-volume curve. An isovolumetric process will look like this. An isobaric process will look like this. And an adiabatic and an isothermal will be somewhere in the middle. So what is this? This is isobaric, isovolumetric. An adiabatic or isothermal would look like a curve going that way. You wouldn't really need to identify between the two of them unless you're a physicist. Or maybe you do, and I'm just stupid, and I don't know how to do it. What's the second law of thermodynamics? It's pretty damn simple. If me and David held hands for 20 minutes, what would happen? Well, first I'd fall in love with him. And then what would happen after that? Our hands would be at equal temperature. Why? Because objects at different temperatures will continue to transfer energy until thermal equilibrium is achieved. That's the second law of thermodynamics. Right? One more thing. The entropy of the universe is always increasing. That's it. That's all I got to say about thermodynamics.
Is there a third law of thermodynamics?
I think there is. I just don't have it written down. Just doesn't exist in my book. Okay, the next chapter is, so we have about like 10, 15 more minutes until we're done with lecture. The next chapter is fluids. Here's what I'm going to say about fluids. No. All right, next is electrostatics and magnetism. All right, so let's do electrostatics. Chapter 5. If you're mad about me not teaching fluids, no. Chapter 5. Electrostatics. Charges, right? The first thing you need to know about charges is, what is one elemental charge? Or an electron charge, right? Is 1.60 times 10 to the negative 19th coulombs. That is one charge, right? So the charge of a proton, or QP Mayo, right? Anyone?
Yes.
QP is positive E, and QE minus is negative E. Charge of a proton, charge of an electron. Positive 1.6 times 10 to the negative 19th, negative 1.6 times 10 to the negative 19th. Insulators and conductors. So insulators will pick up charges and do what? Absolutely nothing. They are the pillow princesses of physics, right? So an insulator, if it picks up a charge, like let's say you rub it against something, it picks up a couple negative charges, they're just going to concentrate wherever you rub them, right? They can do absolutely nothing with it until you do something to them, right? You have to do all the work here. This is an insulator. What is a conductor? A conductor is going to take what you give it and just do the work for you, right? So a conductor, so let's mark the spot where we added the negative charges. We added the charges right here. They collected right there. A conductor, we put the charges right there. They just went absolutely everywhere, right? So that's poor transfer, and this is good transfer, right? Coulomb's law, probably the highest yield thing in the whole chapter. Coulomb's law states that if you have two charges, there's an electrostatic force between them, right? There's some sort of force between them of attraction or repulsion or whatever it is, right? And that attraction or repulsion is equal to, what is it, FC? FE, sorry.
See centripetal force?
Yeah, it is. Is K1, K2 over R squared.
I think you.
Sorry, K, my bad. Not K1, K2. K, Q1, Q2.
Yeah.
K, because there's a different one that's K1, K2 over R squared. There's a different thing. What is K? It's a constant, obviously, right? Because what did I say before? How do you turn a proportion into an equation? You add a constant, right? So before you have an equation, you have a proportion. So you say that FE is proportional to Q1, Q2 over R squared. Then you do a bunch of experiments with these things, and you calculate a constant. You add the constant, and that becomes your equation. So before that, it's a proportion, where you say FC is proportional to both the charges, the magnitude of both the charges, and inversely proportional to the radius squared, right? Okay, so what is K? K is 8.99 times 10 to the 9th. Newton meters squared per, what goes on the bottom? Coulombs squared. Why? Well, there's newtons, there's meters squared, and there's coulombs squared. Right? And what's the radius? It's the distance between the two charges, right? So they might give you a question. Here's a charge plus E, and here's another charge plus 3E. What's going to be the force between them? Well, it's going to be K times 3E squared divided by the distance between them. Let's say it's 1 meter. 1 meter squared. And then you do the substitutions, you figure it out. That's simple, right? There is a equation for electric fields. I don't believe I've ever used it. Don't think I've ever used it on the exam, right? Field lines. Field lines. Field lines. Field lines. Basically, what's a test charge? It's a positive charge. It's an indescribably small point charge that's positive, right? So a field line is basically what happens to a test charge if you drop it inside of that thing, right? So here's a positive source, and I drop a test charge right in the middle of that positive source. What's going to happen? It's going to get expelled out, right, in every direction. So the field lines of a positive force are dispersed outwards in every direction. Contrary to that, the field lines of a negative field, if I drop a test charge in the middle of that, it's going to bring it in. So the field lines of any single thing are what happens to a positive test charge when you drop it right there, dead in the center. Whew. What is the equation for electrical potential energy? Anyone know? U equals K Q over R. What does that mean? I don't know. Go find out and tell me. That's all that's written in my notes. Literally, I just wrote that out of nowhere. See why, like, and the funny thing is, here's the funny thing. I can't even say I was bad at physics. You know why? Got a perfect score on the section. I don't know how, but I don't know what crack I was on when I took the exam. Well, I do know. It was about 300 milligrams of caffeine, but it happened.
Maybe you just handled physics on the test.
I didn't have that much physics on the exam. And most of the physics that I had was like power and kinematics.
Exactly.
Yeah.
Is it always like that?
No. you wish. You would have believed.
I do practice questions and I actually see a lot of radiation.
Uh, I'm not going to talk about magnetism because I've literally never seen questions about it. And that's the end of the chapter. Because the rest is magnetism. And also stuff that you don't need to know, like calculating like the magnitude of acceleration of a blah, 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 whatever. Like if you drop a charge at what like velocity is going to hit your mom in the head, like in Serbia, you know. So, all right. But one thing I am going to say is that there's a really, really common question about electrostatics that shows up all the time that is really simple. And I don't know why people constantly get it wrong. So I want to see how you guys do, right? You have an electron beam, right? You have an electron beam. One end of this is an electron beam, and one end of this is a proton beam, right? Over here, you have a field of negative charges. And over here, you have a field of positive charges. I want you guys to tell me the path that an electron is going to take and the path that a proton is going to take. They're going to be opposites, right? So let me draw two paths, and you guys tell me what you think. Let me draw a couple paths, right? So the electron, right, is going to go like, right? And the proton's going to go like, right? That makes total sense. And that has to be correct. No, it's wrong. Why is it wrong?
Does it have to go to the bottom?
Why is it wrong? No, someone explain why it's wrong. Imagine that these aren't canceling each other out. They're magnets. They're not like fields that are canceling one another out. What's a neutron going to do? It's going to go straight through the middle, right? But why is this wrong? It is horribly wrong. And it's such a simple thing that everyone forgets. I forgot it the first time I did the question. They're shot at different points. The electron goes first and then the proton. No. Think really hard. Forget all of... You guys understand what's going on down here. It's something down here.
They can't be together?
No.
They're already attracting each
No.
Cancel each other out.
No. What's the difference between an electron and a proton? One's positive, one's negative. What else? Size. The mass. The mass. The electron is going to go like this. Because it's so light, it's going to get carried away immediately. But the proton, it's heavy. You have to give it time. You have to give it time to move. Right? The electron's going to come out and just go zoom, just in the direction of the positive charge. Right? That is such a core, fundamental idea of a question like this, and every single MCAT student gets it wrong the first time they see it. Every single one. Because you're so trained to think only in the terms of electrostatics, you forget completely about the mass. The electron's going to come out and just zoom into here because it is so light. It's like blowing a feather and just like sending it into the universe. The electron's not even going to make it out. It's just going to go straight to the positive terminal. The proton's going to come out, and since it has a momentum going forward, you're going to be able to bend it this way. It's almost like kicking a soccer ball, right? This, you're like kicking a cell. God knows where that's ending up. All right, one more thing, and then we'll close out this chapter. This is another really, really high-yield question. This comes up a lot more often than the question right here, but it's a completely similar discussion, right? I have a 1 coulomb sphere right here, a positive 1 coulomb sphere, and I have a negative 1 coulomb sphere right here. And I drop a positive charge right there. And I drop it. Where's it going to go? Straight down the middle. Because it's going to get repelled from here and attracted here. Oh, no, sorry. My bad. It's not going to go straight down the middle. If they were equal, they'd go straight down the middle. My bad. I thought of another example. The positive charge is going to go like this, towards the negative, right? So let's say that this is path A. This is path A where it was positive 1, negative 1, right? Same sideways trajectory, right, from this, but a heavier one from this. It's just going to be steeper, right? You guys get that, right? Now, how did they complicate this? Where's it going to go? You got to draw a vector diagram, right? You got to draw a vector diagram where this thing's going to push it this way. This thing's going to push it down at what? Like half that. And this thing's going to push it towards it at half that. How do you figure it out? You got to break up the vectors into their components, right? So let's say that this, so we're going to add up all of our dotted lines. So we have about that. Now I can get rid of this. And now this is going to disappear with half of this. And it's just approximations. You know what I mean? And then this is going to amplify that. So this is going to go even further, right? And then this is going to add on to here. So it's going to be about like this. Something like that. And they're never going to ask you, like, there's never going to be like two of them that are super close this way. They just want you to draw out the vector diagram, think about it, and where are you going to draw the vector diagram? Not on the damn computer. You have a sheet in front of you during the exam, right? So just break it down, take a second, figure it out, because people see this, it's like, oh my God, I can't do it. Like, no, you can figure it out. It's all right, right? Okay? So that's a very common question in electrostatics as well. And that's about as complicated as questions like that get, right? Well, that's about it. And then when we come back later, I'm going to let you guys decide. We can either move on to circuits, and then after that, I think is sound, and then light and optics. We'll do sound. Optics is definitely another no. And then after that, it's mathematics. And I actually don't have notes for mathematics because the mathematics on the MCAT is really simple. That's it. That's everything I can teach you. So other than fluids, optics, and chapter 8 of general chemistry, and then psychology, I'll just add these together. Sometimes it just does that. But if we get through physics, I'll just continue with the rapid review series. And then I'm trying to figure out how I'm going to record, like going through the AAMC sample exam, because I really want to do that. I think I'm going to have to do it on my laptop. I'm going to order like a mouse and everything to make it easier for me. But I think I'm going to do it through like a video capture thing so that I can put audio over it as well. I'm just going to hook my microphone up to my laptop, and then we'll do it that way. And we'll go through that. I'll upload it. It'll probably be like a 5-6 hour video of me going through it. So what we're going to do is I want to do it in front of you guys. So we're going to pick... We can use this lecture hall. I'm just going to sit right there, and we're all going to gather around the laptop, like a little Socratic seminar, and we'll go through the exam. And then we'll do that over and over again, and then we'll be done. That'll be it. So thank you guys so much for coming, and I hope to see you at 6 p.m. Oh, and for everyone watching, thanks for all your support.